Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UG's lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics, which is in the first semester of the degree program as the first paper. We have been listening to the concepts related to the electronics part of the paper. This lecture is the 49th lecture. In the last lecture, we have learnt how to draw an equivalent circuit for a transistor. It's mainly meant for circuit analysis. Today's lecture, we are going to strengthen our skills by learning two theorems. I would like to teach one theorem exclusively in this lecture. Maybe if time permits, I will give introduction for the second theorem. And these theorems are very much useful for the circuit analysis and simplification. Before we start today's lecture, I would like to give the session outline for today's lecture. In this session, we are going to see the network analysis. We are going to learn about an important theorem called Thevenin theorem. The Thevenin equivalent circuit to find a Thevenin voltage, which is represented as ETH, and how to find the Thevenin resistance, which is represented as RTH. We are now learning how to draw the equivalent circuits for the electronic components and how do we analyze the circuits for various simplification techniques. We have already come across the network simplification when we learnt the electricity topic. In electricity, we had only the resistors connected in various manners, and it was just sufficient for us to use the two network laws. We call them as the Kirchhoff's laws, Kirchhoff's current equation or current law, and Kirchhoff's voltage equation or voltage law. These two laws we have used for simplifying the electrical circuits in which the resistors are the basic units. But in electronic circuits, we have various components, and the p-n junctions are nonlinear devices. Though the Ohm's law is very much useful, it's very true for the resistors that are used in the circuits, but as far as the junctions are concerned, they are non-ohmic in nature. So simply having the two Kirchhoff's laws in hand along with the Ohm's law, we may not be able to simplify the circuits effectively. For that purpose, we are going for the network analysis with some theorems. So let's see why the network analysis is first of all important. The need for network theorems. Solving for currents and voltages in multi-loop electric circuits can be quite complicated, and particularly for AC circuits. The voltage law and current law always apply, but using them may lead to long system of equations. Certain theorems help with network analysis. Now it's time for us to see what are the network theorems available so that the simplification could be done effectively on the circuits. Let's see some of the network theorems that we have for this purpose. Some of the fundamental theorems of network analysis are the superposition theorem, Thevenin's theorem, Norton's theorem, maximum power transfer theorem, substitution theorem, Millman's theorem, reciprocity theorem, etc. Apart from that, we have lots of other theorems also. When we take electronics as a core course and want to do higher studies on electronics, especially in network analysis, we have to learn about all the theorems. But this course is a basic course which touches upon all the aspects of current, electricity and the charges, etc. So, just an introduction of the network analysis is given with the two theorems included in the curriculum. Let's see what are the two main theorems that we have for this program. We are restricting our discussions to only two theorems which are most commonly used, namely Thevenin's theorem and Norton's theorem. And in today's lecture, I would like to elaborately cover the Thevenin's theorem. First, I will state what the theorem is and how do we effectively implement the theorem in electrical circuits, and then if possible I will take up one example problem for understanding how this theorem is used. So, let us see what the theorem is. The Thevenin's theorem can be used to analyze networks with sources that are not in series or parallel, reduce the number of components required to establish the same characteristics at the output terminals, and investigate the effect of changing a particular component on the behavior of a network without having to analyze the entire network after each change. Now, for what we could use the Thevenin's theorem? We are looking at the two-port network analysis. So, let us have a look at the two-port network analysis and how the Thevenin's theorem could be used. Actually, when we say Thevenin theorem is used, we will use a Thevenin equivalent circuit. We will remove certain components in the circuit. We will not go much into the details of the circuit, but we will totally remove a part and replace it with a circuit called Thevenin equivalent circuit. So, it is like knocking out something from a complicated circuit and implementing a simple equivalent circuit. How we have drawn equivalent circuit for a transistor with a current source and a voltage source, or current generator and voltage generator. In the previous lecture we have learnt the same way. Here also we will remove a particular section altogether and replace it with a very simple Thevenin equivalent. So, let us have a look at the Thevenin equivalent and then we will try to state what the theorem is. Any two-terminal DC network can be replaced by an equivalent circuit consisting of a voltage source which is represented as ETH and a series resistor represented as RTH. Here the suffix TH means the Thevenin. So, the voltage, Thevenin voltage and Thevenin resistor. So, that is the meaning of ETH and RTH. Now, the statement is represented here as a diagram. There are two networks, network 1 and network 2, and A and B are the 2 points we have taken which connects the two network. If we want to replace the network 1 entirely, we may be having lots of resistors and lots of PN junctions and lot of voltage sources, current sources, etc. in this network, maybe in the series, parallel and mesh connections, matrix connections, etc. But we don't mind all that. We will simply replace this network 1 with an equivalent which is shown here. Across A, B, no, we have a circuit which has this ETH and RTH connected in series. Now, the main part is how do we find this ETH and RTH? That is a real challenge here, but that can be easily found. We will see how the ETH and RTH could be calculated. Calculate the ETH by first returning all sources to their original position and finding the open circuit voltage between the marked terminals. This step is invariably the one that will lead to the most confusion and errors. In all cases, keep in mind that it is the open circuit potential between the two terminals. So, how do we find the ETH? We have to keep the circuit across the two terminals where we wanted to remove one network. So, we have to keep everything in the original condition. What does that mean? It is open circuited. All should be open circuited in that section, and then we have to measure what is the voltage drop that is existing between the two terminals. So, by doing that, we find out the ETH. We should not mind about anything. We should keep the circuit in the open circuit condition, and across the two terminals we need to measure the voltage. Then how do we find the equivalent resistance? For that, what is the condition? Let us see. To calculate the RTH, first set all sources to 0, that is the voltage sources are replaced by short circuits and the current sources by open circuits, and then find the resistance between the two terminals. If the internal resistance of the voltage and or the current sources is included in the original network, it must remain when the sources are set to 0. So, the Thevenin resistance is connected by the short circuiting of the two terminals. So, let us see what is the short circuiting means. Before that, let us have a look at the open circuited condition for measuring the voltage. This is the open circuited voltage. In the network 1, the two terminals are just kept open circuited. We do not connect anything across the terminal A and B, terminals A and B. So, it is the open circuited condition. Now, we need to have an understanding of what is the open circuited condition for measuring the current. For that, we need to keep certain things in the short circuited form. Let us have a look at the equivalent circuit after a short break. Welcome back. We are discussing about how to calculate the Thevenin equivalent resistance. The voltage is measured by open circuited condition. The same manner, how do we find the Thevenin equivalent resistance? We need to have a look at the circuit, typical circuit, and understand how do we measure the Thevenin equivalent resistance. So, let us take a practical circuit and see how the Thevenin equivalent resistance is measured. To find the Thevenin equivalent resistance RTH, the voltage sources are replaced with short circuit, the current sources are replaced with open circuit condition. And though we mention these 2 points in words, it is well understood when we have a look at the circuit that is shown here. Have a look at this circuit. Here we have a voltage source V1, voltage source V2 and voltage source V3 and the two current sources I1 and I2 here, and resistors, various resistors are also shown here. The two terminals are AB. When we want to measure the RTH, what we should do, the first condition, voltage sources are replaced with short circuit. So, we need to just remove the voltage sources and short the terminals. So, that is what is done. V1 is removed and short circuited, V2 is removed and short circuited, V3 is also removed with a short circuit. And what about the current sources? Current sources are replaced with open circuit. Have a look at the two current sources. I1 see is just open circuited, we need to remove and open circuit, keep it in the open circuited condition. I2 is removed and keep the section in open circuited condition. In this condition, we need to measure the resistance across the two terminals AB. This could be done using a ohm meter practically when we want to have the value, or it could be calculated using the typical equations we use for resistance in series, resistance in parallel, series parallel, using some symmetry technique. So, we are well equipped to find the equivalent resistor, because this has been discussed in the initial lectures. So, now we have got an idea of how to find the Thevenin equivalent voltage and Thevenin equivalent resistance. Thevenin equivalent resistance just now I have explained. Before the break, I have explained how to find the Thevenin equivalent source or potential. It is to be measured in the open circuited condition. Now, with these two values, now we will typically be able to replace the network with the Thevenin equivalent network, which has a source and a resistor in series. This is how the equivalent circuit is now taken. See here, the network 1 is replaced and it is replaced by the very simple Thevenin equivalent circuit. Of course, we have calculated the ETH and RTH by imposing some of the conditions. The network 1 could be a very messy one. We do not know what sort of connections are there, but nevertheless, by implementing the two conditions, we were able to remove the entire network with a Thevenin equivalent like this. Now, I hope we have got some idea of what is Thevenin theorem. The Thevenin theorem is actually replacing a particular section with a Thevenin equivalent circuit. The Thevenin equivalent circuit consists of a Thevenin equivalent voltage source and a Thevenin equivalent resistance. How do we find the Thevenin equivalent voltage and Thevenin equivalent resistance? That I have covered so far. With this, I think we are well equipped to take up any circuit for simplification. We will get the greater understanding only when we take a particular problem in which the Thevenin theorem is used for simplification. We will do that now. We will take up this example, finding the Vx, the voltage Vx, which is marked here across AB. So, find Vx by first finding Vth and Rth to the left of AB. So, the problem itself suggests you first find the voltage, Thevenin voltage. Here the instead of E, we take it as V, but it is having the same meaning. It is the Thevenin voltage equivalent source and Thevenin resistance, equivalent resistance. And when we have a look at the circuit, we infer that it has a voltage source of 30 volt and 3 resistors to the left of the point AB, 12 ohm, 4 ohm and 6 ohm resistors connected in this T form, and the 2 ohm is the output resistor, and the question is we need to know what is the voltage that is dropped across the 2 ohm resistor. We are going to use the Thevenin method for finding the Vx. We will approach this problem step by step to implement the Thevenin equivalence. To find the ETH, now we use the conventional notation ETH. First remove everything to the right of AB. What was to the right of AB? Have a look at the previous diagram. It was only the resistor here. That was actually the network 2 we showed in the previous slides. So that is totally removed, and we are attempting to find the voltage ETH. So notice that there is no current flowing in the 4 ohm resistor. AB is open, thus there can be no voltage across the resistor 4 ohm. When we have a look at this circuit, the voltage source produces current to flow through the 12 ohm and the 6 ohm resistor, and the current returns to the source. Though the 4 ohm resistor is in the circuit, no current flows through the 4 ohm because it does not have a path, closed path. So there is no potential drop across the 4 ohm. Though it is physically present, electrically it does not have any meaning. The point A to the right of the 4 ohm could be taken as a point to the left itself, because this is electrically dormant in this condition. Now it is like the 30 volt is dropped across the 12 ohm and 6 ohm. What is across the 6 ohm is appearing across the two terminals AB. So it is like a voltage divider, 12 ohm and 6 ohm. So we want the voltage across the 6 ohm. So this is the voltage divider circuit equation. So we find that value as 10 volt. Out of this 30 volt, 10 volt is dropped across the 6 ohm and 20 volt is dropped across the 12 ohm resistors. This is a simple calculation which we have done already in one of the earlier lectures. Now after finding the ETH, what we should do? We need to find the RTH. Let us make an attempt. We now deactivate the sources to the left of AB and find the resistance seen looking at these terminals AB. As explained, we have to short circuit the voltage source. That has been done, and these are the 3 resistors. We need to find the equivalent resistance, that is called the Thevenin equivalent. When we have that calculation, that RTH is done here like this. The 12 ohm and 6 ohm are in parallel, and that combination is in series with 4 ohm. So that is also calculated here. Now we have found the 2 terms necessary for implementing the Thevenin circuit in the problem. We have found the values of ETH or VTH, whatever it is, that was 10 volt, and RTH is also calculated now, that is 8 ohm, but we have imposed the conditions that we have done. Here we had only the voltage source that was short circuited. We have found the Thevenin equivalent resistance as 8 ohm. Now it is time for us to replace the entire network to the left of the point AB with the Thevenin equivalent circuit. See, after having found the Thevenin circuit, we connect this to the load in order to find Vx. See, the entire section is replaced with the Thevenin equivalents VTH and RTH, and the circuit has become very simple. Now it becomes very easy for us to calculate the voltage that is dropped across the 2 ohm resistor. First, this is again a voltage divider circuit. The 10 volt is divided across the RTH and the 2 ohm resistor. So we need to find the potential drop across the 2 ohm resistor. It is done here. This formula is also a quite familiar formula. It is a voltage divider equation. So we find the voltage drop across the 2 terminals AB with the 2 ohm resistor at the output side as 2 volt. This can be done by finding the current in the equation and then the potential drop across the 2 ohm. That is another approach, but it is not necessary. That is a 2-step process, but this gives us a single step approach for finding the value. So, we have done a problem now to implement the Thevenin equivalent circuit for simplifying electronic networks. I hope you would have got a good understanding of the Thevenin theorem, because we have solved one full problem using the Thevenin theorem. We have one more theorem, that is Norton theorem. I would like to reserve that theorem for the next lecture. I would like to give the summary of today's lecture before winding up this session. In this session, we have seen the need for network theorems, the different networks theorems that are available, and the Thevenin theorem, and we learned the Thevenin theorem with an example problem. Now, let us test our understanding of what we have learned in this lecture by answering these questions. Discuss the need for different network theorems. State the Thevenin theorem and discuss how to find the ETH or VTH and the RTH in the Thevenin equivalent circuit. We have learnt the different network theorems that are available. We have just had the names only registered in our minds, but learnt the Thevenin equivalent circuit or the Thevenin theorem with some understanding and an example for enhancing the understanding. In the next lecture, I would like to take up the Norton theorem, which is also somewhat similar to the Thevenin theorem, but the way in which we find the equivalents differ. Based on the network simplification, we need to use these two theorems. So, see you in the next lecture with the concept of Norton's theorem. Until then, goodbye.